Okay, great. Thanks, Philippe, for the introduction. Hi, everyone. It's a pleasure to be here to talk about learning from literature extracted synthesis action for organic synthesis. What started this project was the realization that chemistry in the lab hasn't changed much in the last decades. New reactions have been invented or discovered, but the operations in the lab to make those reactions are roughly the same. At the same time, millions and millions of reactions have been reported in the literature. All this data leads to opportunities to accelerate discovery, for instance, by assisting chemists in synthesis planning or even running synthesis for them. With the help of machine learning, all this information should actually enable us to go all the way from the specification of a compound to its automated synthesis execution in the lab. What we have been aiming at is a setup in which a user or even an algorithm comes up with a compound and its synthesis is then launched automatically in the lab. And in this scenario, the chemist can even launch the synthesis from home. The whole pipeline can be split in 3 steps, which I will describe shortly in the next few slides, before then going in more detail later in the talk. So the first step is starting from the compound that one wants to make to determine how to make it in terms of commercially available building blocks. This is the retrosynthetic analysis. And we can represent it in a tree where the nodes are the compounds to make and the children are potential precursors to produce this compound. When we have the retrosynthetic tree for the desired compound, we can go to the next step and determine for each separate reaction step how to make it in the lab in terms of operations done by chemists. After that, we take those synthesis actions and convert them to instructions that are specific to a robotic installation in the lab so that we can launch the automated synthesis. If I put these 3 steps together, this represents, in principle, what I will be talking about in this presentation. So I will go over all 3 steps with an emphasis on the second one. And to keep it clear where I am, I will keep this at the top of the slide. So let me come back to this first step of the retrosynthetic analysis. As many of you probably know, there are many different approaches to tackle this problem, and I will be talking about the approach that we take at IBM. And the question is basically, given the compound on the top, how do we get there? In other words, we want to determine what's on the left of this reaction arrow. And in our group, we have been looking at this problem in terms of translations and specifically tackling this translation with language-based models. So in principle, we take the product described as a smile string, and then we convert it to what I sometimes call a sentence of atoms that we then translate with a transformer model to another sentence of atoms. So basically, we go from the language of chemical products, so to say, to the language of chemical precursors. And then from this from the output here, we can get back the structures of the precursors, or one among many different sets of precursors, and we can even get different suggestions. Then, in order to get the full retrosynthetic tree, we apply this iteratively until all the compounds are commercially available, and we can also use a set of selection criteria. Having that, we can then go to the second step, where we take one reaction step and want to determine the actions to make that in the lab. As an example, we can look at this nitration reaction. So this nitration reaction, it follows a more general pattern or a template for a chemical reaction, basically a nitration at an aromatic ring. And it can give us a good idea of how to make that reaction in the lab if we look at this template. However, usually it will not be exactly the same actions, and it's hard to predict the optimal set that will lead to the success of the reaction in the lab. And ideally what we want is a machine learning model to predict this based on the input. So in other words, we want to start from a chemical equation given, for instance, in the form of a reaction smiles, and then get as an output the operations. And the first problem to do that is that there is no data set where we have in a structured format the reaction equations and the operations or actions. This information is available, but only indirectly. It is available quite often in text form, in unstructured text. So here we have the example of a patent where we see inside some addition, then stirring, concentration, extraction, drying, and so on. So if we want to use information like that in order to train the model for predicting the actions to make in the lab, we will first need to extract this information from text. So what we did was we took a detour and trained a different model to extract those actions, which is what I'm going to talk in the next few slides. So basically what we want to do is to convert some text into operations. And the first question is, what are these operations that we are interested in? And there we really wanted to stay close to the chemistry and have operations that are close to the actions that chemists do in the lab, such as adding compounds, stirring, filtering, extracting, concentrating, and so on. And after a few iterations, we came up with roughly 20 different actions, each of which is associated with a few properties. And if we look at the addition action, for instance, the properties that are linked to it would be the what to add and in which quantity, potentially the temperature at which it is being added, over how much time it is being added, and so on. So with these actions, we now have the following task, where in this case, from this sentence of experimental procedure, we would end up with one addition action and one stir action. To do it with computers, we have potentially two approaches. We can use a rule-based model, which will follow a set of rules to get those actions, or we can rely on a fully data-driven machine learning model. And if we look at the rule-based model, the advantage is that it requires no training data at all, but then it is usually not very robust and it is hard to improve. On the other side, for the machine learning model, we don't have any training data, but if we have some, we can improve it by improving the data. So what we ended up doing was to generate an initial training set of data with the rule-based model to train the machine learning model. And I will now go very shortly into those two models. So first, the rule-based model, which basically follows a series of steps. If we have a sentence, it will first split it into different parts, look for the verbs, for the compounds, for other properties, and then also determine all the relationships between all of them. In practice, this can be very hard because looking at, for instance, a verb like remove, it can mean filtration, or it can mean evaporation, or even other actions depending on the context. Then we have words that look like verbs but are not verbs. And also, there is not always a one-to-one correspondence between verbs in the sentence and the actions that we want to extract. Despite this, we generated actions with this rule-based model for 4 million sentences that we then use for the machine learning model. For the machine learning model, we also relied on a transformer model by formulating the task as a translation between the experimental text and a readable representation of the actions. So when training on those 4 million sentences, this worked actually quite well. And I have 2 examples here, one of which is correct with 1 addition action and 1 stir action, and another one where the rule-based model and the machine learning model make the same mistake. They basically are not able to detect the action to change the pH in the second half of the sentence, which doesn't have any verb actually. So in short, the machine learning model that we trained like that was as good and as bad as the rule-based model. So we needed to look at ways to improve it. And what we ended up doing was to refine on manually annotated data that we generated with a platform that we designed for that, where basically in the browser, a user would see the sentence to annotate on the left-hand side, and then the actions extracted by the rule-based model, where they would then be able to update them, add missing actions, and so on. And in this manner, we generated roughly 1,700 additional sentences of higher quality, with which we then fine-tuned the initial model. And this, in the end, worked quite well. So this combination of initial training on automatically generated data and then fine-tuning on higher quality data. So having this model, it then enabled us to come back to the task that we were actually interested in. As a reminder, we wanted to generate or to predict the actions starting from a chemical equation. And so with a set of experimental procedures from the patents, and using this paragraph to actions model that I presented earlier, we were able to generate such a data set and train a model on it. If I go very shortly in detail how it looked like, so starting from the chemical equation and the experimental procedure, we would extract the actions, process them, and then the task of this new model would be to predict the actions starting from the chemical equation. Here, this is roughly the same, and I just wanted to highlight that this was quite an involved process to generate this data, starting from over 3 million reaction records, ending up with 700,000 that we then use for training, again, a transformer-based model. And that's basically it for the second step. And I'm coming to the third step. I see that I have 1 minute left, so I will be fast. Basically, we then integrated it with a robot and a cloud-based platform where the user can start from the compound that they design, then do everything assisted with AI, the retrosynthesis, the determination of the actions, and then launching it on the robot, even remotely. So in summary, that was all. So again, starting from the desired compound, we generate the retrosynthesis, then the actions, and then we can schedule it on the robot. All of it from the IBM RxN website, where you can also freely try those models out. And with this, I would like to thank my collaborators and all of you for your attention.
Thank you very much for this nice talk. Are there questions? And there in the back.
Yeah, thanks. Great talk. I just wanted to ask, Basically, two questions regarding the manual data creation process. So I remember from my organics lab courses that it didn't work out every time. So I myself was not able always to translate the procedure, and also even in these simple instructions there were ambiguities. So I just wanted to ask, how often did you encounter that? Or
so it's a very good point, and so two answers. So first, it is always a good idea for the chemist to check the actions before launching the execution, and this is commonly what we do. The actions, usually from what I heard from my colleagues, they are a very good starting point, and then this can be improved. Then it is true that sometimes the reaction doesn't work out, and this is as you would experience, just what you were saying, that even though you follow what seems to work from the literature, the reaction doesn't work.
If I could just quickly follow up, I think my question was rather that did you encounter, for example, examples where AI and human input labeling were so different that you maybe had to reiterate and saw that the human actually itself did an error whilst...
So are you talking about the extraction of actions
Yes.
from the text? Okay, yeah. So this, we did it in two separate steps. So we had an initial generation of the model and then a second also round of annotation. And by looking at examples, you tend to see where the model fails. And then we biased the selection of the data to annotate based on the examples where we knew the model wasn't yet good enough. And for instance, I showed the example of this pH action. Usually with the rule-based model and also with the first generation of the machine learning model, those were not extracted always adequately.
Thanks.
Thank you.
Thank you very much. Are there other questions? Okay, so thanks again.